So
Okay.
yeah.
Alrighty. So let's see. Yep. Okay. Okay. The recorder has started already, so I'm gonna get started with the lecture. This is the first day of the second 8-week half semester. Not that you guys would care or know about it, because I don't think anyone here is taking first or second 8-week classes, is it? Is anyone taking half semester classes? Okay, there are a few, okay. So you guys know this, okay, it's the transition between first and second 8-week classes. But this class is a full semester class. I'm just keeping track to make sure that I have enough time to talk about all the things that we need to talk about. All right, so what we'll do is the usual thing that I do, which is start with a homework assignment, and then we'll go back and talk about the concepts and things that you need to know to do the homework, okay? So I'll start with a homework assignment, make sure you guys understand what you need to do, and then we'll go back and talk about the concepts, the tools, you know, and basically the how-tos of doing things, you know, with this particular homework assignment. Okay. So the homework assignment is called Egg Hunter, which is not religious. There's no religious connotation or reference in this case, okay? And if anyone looks up, you know, if you think it is related to a particular religious day, look deeper, okay? Because if you think about it, it really should not have anything to do with eggs or bunnies,
Okay.
right?
That's so logical. So logical. Yeah. Eggs and bunnies.
Eggs and bunnies.
Well, it does make sense.
Not eggs. What's so?
Well, if you think of the spring solstice and rebirth,
Then it starts to make sense.
then it makes
Sounds
sense.
like an LSD trip or something.
and then they're all colorful too.
Exactly.
Right?
Yeah.
Yeah. Somehow it's related to religion.
Well,
Okay. So this is your homework assignment. I'm giving you a file to start with. So what I'll do is I'm going to complete at least the first half of the homework assignment to show you the steps. Okay. So the steps would involve this. You have to download a file which is called egghunt.tar.gz. It depends on where you do this from. If you're doing this in Windows, you'll have to just just click it and save the file. If you're doing it in Linux, you can save the file directly into your home directory, and then just do all the other steps, you know, as I do it in class, because I am using a Linux environment. If you're running this in Windows, you would have to download it into Windows first, and then upload it onto the Linux virtual machine to the home folder. We have done this already in the first homework assignment, I think. Did we? Okay. So I'm pretty sure you can kind of take up the steps to do it, but I'm doing it anyway right here. Okay, so you go to a command prompt, Andy would do, and then you just go to your home folder and run the command tar xzvf to decompress the file. In this case, because my browser automatically saves the file into the downloads folder, it is here. So just look for egghunt.tar.gz, and it will decompress the file, the tar file, into a folder, egghunt, and then in the folder egghunt, there's a program called bunny.s. Could have said hare or rabbit or something like that. But bunny is good. So you go to here and then you look up the file called bunny, and this is your homework assignment. So for your homework assignment, the objective is by the time we get to the label check here, I want EBX as a register to have the value of 353880604. Okay, that's the objective. And you can only make use of how memory is initialized in this particular program. So so I'll go through all of those concepts today using different sample programs. So you kind of have to pull all the things together to basically figure this one out. Are we doing okay so far with this homework assignment? Now the only thing you can do is to specify what goes into the underscores. So there's one empty space here, one empty space here, and one empty space here. So your job is to fill in those empty spaces with something so that the objective is accomplished. Are there any questions? Yep.
How lengthy is the amount of code that goes into those empty spaces?
Typically not very lengthy. I would say, it's not going to be much more than 3 space assignments. So they're not going to involve some huge complex expression like this. Okay. Alrighty. So we'll keep this one up, okay? Because I think we'll go back to this and refer to it from time to time. Okay. So the first thing we need to do is to talk about, well, okay, first of all, I'm going to give you a few pointers. Okay, so I've added quite a few links into this particular topic. The first one is the reference manual of the assembler. Okay, so this one will contain the full syntax. Okay, what you need to do this homework assignment, and a whole lot more. Okay, so what I can do is to point out which part is useful for this particular homework assignment. I also included a reference manual for GDB itself. So for those of you who are kind of new to GDB and you need to kind of get familiarized with GDB, this is a manual for that. And then we have addressing mode notes. This one is older, but it is still useful. This one is a newer one, so you might find reading these notes a little bit helpful. We are not going to need arithmetic operations or jump instructions in this case, nor do we need to know how to multiply and divide for this homework assignment. Okay. Are there any questions about the resources available in this topic at this point? Okay. If there are no questions, I will go ahead and take a look at, let's take a look at the assembly instruction first. So we'll go to the assembler reference manual. And this is the official link. This is the official link to the assembler documentation. And if you go back to the program, we have a .text here. And when you go back to the manual, you can just look for .text right here. And then you can look up the meaning of .text. Now, in the fine tradition of GNU, this kind of documentation tends to be a little bit terse. Okay, so what I'll do is I'm going to expand on their documentation and just kind of make sure that we understand what the .text means. In assembly language programming, unlike in C and C++ programming, you have full control over where the code goes and where the data goes. Okay, and .text is basically saying, from here on, I want to specify code, not data. But what that means is the space or the memory that you'll be using up from here on is basically read-only. You cannot change it. That's basically what it means. Is there any question? Okay, when you look at the program, there are basically two quote-unquote books. One book contains the instructions, okay, that's the code, and the other book contains the data, the variables, the stack, and so on. So there are basically two quote-unquote books when you execute a program. You look at the book that contains the instruction to figure out what to do, but the instructions most of the time will involve changing variables, which you maintain in the other book. Now, the reason why we separate into two books is one book is read-only. The instruction manual itself is read-only. You cannot overwrite your own instructions. The other book is read-write because they only contain variables, things that you can change. Is that concept okay? So what .text means is from here on, we don't want to be able to modify memory. It will only be read-only. That's basically all it means. And .text is by default. Okay, when you start up an assembly language program, .text is already by default the one that is being used. In other words, in this particular program, line 1 is redundant. It does not need to be there. Okay, line 2, line 4, and line 5. One starts with a .byte, .word, and .long. These are directives. In other words, these are basically instructions telling the translator, in this case the assembler, which is taking the role of a compiler, and say, I want to reserve bytes and also initialize those byte locations. That's what .byte is saying. .word is saying, I want to allocate 16-bit chunks and initialize those 16-bit chunks. .long is saying, I want to reserve and initialize 32-bit chunks. Okay? So they're kind of like your initialized variables, but not quite exactly the same. because in this case, I'm just saying, hey, give me 3 bytes, okay, the first one, and the following expressions are the initial values of those locations. Dot word, kind of the same thing. I want to initialize 3 word locations. Each word is a 16-bit location, and use the following expressions as the initial value. And dot long, kind of the same thing, except we are dealing with 32-bit chunks instead of 16-bit chunks. And then you can see, we have 1, 2, 0x12, and 0, 1, 2. 1 is in base 10, 1 is in base 8, and 1 is in base 16. And I will leave it to you to kind of decide which one is which one, because these are all standard in C as well. Okay, the different bases. This is also how we specify numbers in different bases in C. Yep.
Can I place comments in there with double slashes, or is it?
You can put comments in there. It starts with a pound sign. So anything to the right-hand side of a pound sign, or the other way, bang,
Yeah.
okay, is to everything to the right-hand side is considered comments and is not used.
It's not used in there.
Yep. Yep. All right. So are there any questions about dot byte, dot word, or dot long? They are used to allocate and initialize memory, and each one is different only in the width of the memory that is being allocated. Yes?
Not giving those numbers, not assigning them to a variable or anything like that?
There's no such thing as a variable in assembly language programming. So we are basically just sticking some bytes into memory. They are not variables. They do not have any name until we get to L1. Then we start to have a single reference point, and that will be a very important reference point. Yep. Oh, sorry. Go ahead. I will let you continue first, and then
You're putting in there, remember, are they all right next
they're
to
all
each other?
contiguous. Yes. So they're all sequential as ordered, as you specify here, and they're also contiguous. So the 3 bytes are right next to each other. The 3 16-bit quantities are right next to each other, and then the 3 32-bit quantities are also right next to each other, and then all the chunks are right next to each other as well. So we have byte, 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 16-bit, 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 32-bit, 32-bit, 32-bit in this case, and they're all contiguous. Yep, go ahead.
Sort of a side thing. I thought bang was an exclamation
Yeah,
point.
that's exclamation point. It's the pound sign. Sharp. Yep.
Okay.
Hashtag.
Yep. C sharp. I'm pretty sure that was an accident. Somebody wrote C++ in a bad way, bad penmanship, and whoever was reading it for marketing purposes would go like, oh, sharp, C sharp. Okay, this is a new programming language.
That's how it became.
Yeah, I'm pretty sure that's what happened.
And it would seem like Microsoft would do that.
Just accidentally. But then we can the next version of C sharp can be D flat. All right. So, okay, now let's go back to the browser, because I want to go back to the browser and be able to find all of these things, right? So you do a search in the browser and just look for dot byte. And here we have dot byte and a whole bunch of stuff. These are all arranged by alphabetical order. Let me just kind of magnify so we can all see. So this is all organized alphabetically. So dot byte is right here, and I'll just open it in a new tab. The next one is dot word. So look for dot word. And the next one is dot long, which is also known as dot int. Okay, so that one actually has 2 names, but we'll use dot long just to be consistent. So now I have 3 tabs here. Dot byte expects 0 or more expressions. Separated by commas, each expression is assembled into the next byte. In other words, whatever the value of the expression is becomes the content of, quote unquote, the next byte. Is that okay? And dot word is about the same. The directive expects 0 or more expressions of any section separated by commas, and the warning part has to do with machines with a 32-bit address space that do less than 32-bit addressing requires the following special treatment. And in this particular case, it is just 16-bit. Okay, dot word deals with 16-bit, and then dot long deals with 32-bit, and it's the same as dot int. So if you click on dot int, it tells you exactly what it does. Okay, but I have a question, because the i386 architecture is byte addressable. So if it's byte addressable and you want to specify, let's say, a 16-bit quantity, which byte goes where? Are you guys
Okay.
getting the point? Okay. So let me give you a particular example here, just so that we can refer to it. So we'll refer to a number or a particular value. Let's say 3B89. Okay. This is the 16-bit value that I want to store into memory. How many bytes do I need? We need 2 bytes. But since the i386 architecture is byte addressable, one byte is going to have a lower address and the other byte is going to have the higher address. So now the question is, which byte is going to contain which part of this number? Okay? Now this is all specified in base 16, which makes it very easy to read. So I just answered my own question a little bit earlier, okay? At least a part of that question. This will take up 1 byte, this will take up another byte. Is that okay? So now the question is the lower byte, the byte that has a lower address, H9, or is it 3B? The correct answer is, it depends on the architecture. There's no right and wrong answer in this case. So there's no really quick and easy fix and go like, oh, it has to be this one. The i386 processor turns out to be a little endian processor, which means the least significant byte is stored at a lower address. The most significant byte in this case is stored at a higher address. Sorry?
It reverses it by chunk, right?
Well,
we would read it one way, but the computer is going to look at it by chunks.
It's organized in a different way, correct. It is organized in a way where the least significant byte has the lower address. It's called little endian. Other architectures, like the 68,000 processor architecture, the entire family, they use big endian. Okay, endian, not Indian. Endian. Okay, so big endian is going to do exactly the opposite. Okay, the most significant byte is stored at the lower address, but the i386 is a little endian processor, so 89 is at a lower address. Okay, yep, go ahead.
I never really understood the reasoning behind it.
Why they're using little endian as opposed to bigger?
Between the two. Between
the two, there's no win. Okay, there's no there's no win-win situation here. Both architecture has something that is really good at, or it saves time, and something is not really going to save time.
Okay.
It comes out as a wash. It really is kind of arbitrary. Okay. Yep.
No, I was going to. There's a book about that, about where that convention came from, and it's actually pretty good. It's pretty fun to read in.
Okay.
Like that.
I will look it up. Okay. Are there any questions about this? Well, can I confirm this using just regular C? Because that is the prerequisite of this class. So I want to see if you guys know how to confirm that the i386 is in fact a little endian architecture. Can we confirm that?
Yep.
Just using C with no assembly code. Sorry, go ahead.
Sure, there's a way, I don't know how.
Okay, so I will show you the how. Okay, let's go ahead and start another terminal here just to show that one. Okay. And I'll just write this program as endian.c. Okay, nothing fancy. And all it's going to take is a 16-bit integer. So I'm going to say short int. I just know that with a 32-bit architecture, a short int is 16-bit. Okay, so that's why I can do something like this. And we'll use exactly the same value, which is 0x3b89. And that's my entire program. I don't need anything else in this program, because I will do exactly the same trick as I did with the floating point number homework assignment. I'll be casting the pointer, do something funky with it, and then dereference it. Okay? So let's go ahead and see how this can be done. So GCC, I'm just going to shortcut it to produce the executable right away, because there's no need to compile in between.
Did you need the G?
Yep, I do. And the dash G has to be before the dash O because you cannot put anything in between the dash O and the file name Endian. Well, might as well put one off just to see that it's going to complain about one thing, okay? Because X is initialized, but it's not used anywhere else in the program. All right, so now we can go ahead and GDB this particular program called Endian. List the program, put a breakpoint on line 6, which is the return statement. Run the program. Nothing exciting is really happening, is it? Okay. So now, what type of number are we looking at here? Let me. It's all in decibels. So there goes. That answers the other question that I had a little bit earlier. And because the question only had 3 choices, by answering 2 of the 3 questions, the last one is also answered as well. Because the questions was which one is base 8, which one is base 10, and which one is base 16. By indicating which one is base 16, which one is base 10, now you know which one is in base 8. All right. Okay, so what are we going to do with this program? Well, we want to look at the Endianness of the processor. So the way to do it is to do something like this. Cast it to a char, okay? And cast the address of X into a char pointer. And I'm not going to print it out in base 10 because it really is not easy to read. Print/X will print it in hexadecimal, and we now have the 8-9. Okay, that refers to the first byte. Okay, but just to confirm, okay, how do we get to the most significant byte? To get to the most significant byte means I'm going to add 1 to the char pointer. I'm just adding extra parentheses here to be sure that I am adding 1 to a char pointer and not adding 1 to an int a short int pointer, just to be sure. Okay. So when I do this, I should get the most significant byte, which is the 3B. So this is a quick, easy way to confirm that the Intel processor is in fact a little Endian processor. Are we okay with this? Okay, all right. So with this one out of the way, let's go back to the program that we are supposed to work on for the homework assignment. So I have just explained line 1, line 2, line 3, line 5, okay? What I have not explained is line 4. Line 4 is the definition of a label. In this case, the name of the label is L1. Not exactly creative because it really is just a label, okay? There's no particular reason why I have to call it anything else. A label is a bookmark, okay? So in this particular program, what we are doing is we are allocating some bytes and initializing those bytes along the way. The second line is going to initialize 1 byte, 2 bytes, and 3 bytes. Line 3 is going to initialize 6 bytes altogether, right? 2 bytes, 2 bytes, 2 bytes. And then the line 5 is going to initialize 12 bytes altogether because dot long, each one is 32 bit wide. So 1, 2, and 3. These are all contiguous. So if you're counting the bytes, okay, I don't know where the first byte is, okay, by the way. There's no way you can actually predict where the first byte is, okay? But in terms of relative location, this is the first byte, second byte, third byte, fourth byte, fifth byte, and so on. They're all contiguous. The label L1 is nothing more than a bookmark, and that bookmark is indicating this location. To be more exact, it is actually the address of the least significant byte or the lowest byte of whatever this thing is. Are we doing okay so far with this? So L1 with a colon is a way to define a label. Now, when we talk about a label in assembly language programming, a label is nothing more than a symbolic name that has a number associated with it. Okay? What can you do with numbers, integers?
Use arithmetic.
You can use arithmetic on it. You can add something to it. You can subtract something from it. You can multiply with something else. You can divide it. So all of those operations actually apply to L1 as well. Okay. So let's assume that we are always reading from left to right, and this is from the memory layout perspective and not from the value perspective. Okay, so that means that this one you have to be careful, this one you have to be careful because of the endianness of the processor. Now, if we look at this from the layout perspective, this byte here, whatever byte is taking up this portion, has the address of L1. What about the address of the next one? L1 plus 1, right? Because L1 is just a number. It's just a page number, okay? It is a bookmark corresponding to a page number. The next page is plus 1, right? What about the previous one? What about this byte here? Minus 1, L1 minus 1, exactly. So by knowing the name of one byte out of those many bytes, now I can assign, I know how to get to all of the other bytes. Are we doing okay so far with what a label is and what you can do with a label? Yep.
Does L1 mark the most significant bit or the least significant?
It is in terms of address. It is it's the lowest byte of the .long 2-3.
Okay.
Yep. So whenever you define a label, it is only seen from the memory layout perspective and never from the actual value perspective.
Like on the left, you get the lowest memory address, and then you get the higher memory address.
The most significant byte has the highest address. The least significant byte has the lowest address.
So like in the picture, so
In the picture, this is all according to the memory layout, not according to the value.
So, if we were to store that number, and it was being stored into 23, just as a location, L1 would be 89, and then
That is correct.
L1 plus 2 or plus 1 would be 3B.
Yep. In fact, what I'll do is I'll give you another sample program to illustrate those points. Okay. So I'm going to give you many individual sample programs, and together they will give you enough information to do the homework assignment. Okay. So you gotta look at all of these sample programs. So I'm going to give you another program, and we'll just call that mem1. Okay. .s, and this is just a program. I'll just do L1 here .long. And I'll give it some gibberish value here. Okay, I think this is a good one. It only has 6 hexadecimal digits, and yet it is a .long. So now the question is, where are the missing bits? And what are they? They're zeros, and where are they?
On the right, all the way down.
All the way to the right.
Well, so
The implicit zeros.
In the fourth.
Okay, are they the most? Are we putting the zeros into the most significant portion or the least significant portion? That's the question.
most significant.
The most significant, because exactly. Okay, so you can always pad zeros on the left-hand side when you look at the value of a number. Okay. All right. So this is our program, and I don't really need to make this program run, but to shut up the assembler or the linker. Actually, in this case, I have to give it something like this, okay? And we'll just give it a no-op instruction. Okay. In other words, the purpose of this program is not to run it to see what it does, but to understand how memory is laid out. Okay, and also the introduction of GDB commands that you will find useful for this particular homework assignment, at least some of them. So we'll do an AS-G flags, G stabs like that. It's kind of doing the same thing as a -G for the C compiler, okay, just so that we can use GDB once we have the executable. So make sure that you include -G stabs, -O, to create the object file. And this is the input file, which is mem1.s. Oh, okay. You have to supply the name as well. There we go. All right, so I use mem1.s as the input file, and it creates an output file, mem1.o, which is the object file. In GCC, you don't have to name the object file, but in the assembler, yes, you do have to mention the name. And the linker is LD, okay? So the linker will you can specify the output executable name, and then the input is the .o file.
Oh, but that makes sense.
Yep. So basically, you'll be running these commands quite a bit when you're writing the program. All right. Any questions about this part? If there are no questions, we complain about us. think I forgot one thing. My program just got erased because I ran the first program incorrectly, so I'm gonna have to retype the whole program.
Really?
And probably won't be using the same constants, right? Does anyone remember?
Yep.
I can always play the video again.
1A9 7 F6.
F6? Ah, close enough.
Yeah, you need L1 before that.
Oh,
No, clearly not there.
okay. Ah. All right, there we go. Okay, so here's the program, and we'll repeat the correct command. There we go. dbman1, and here's our program. I'm going to put a breakpoint on line 8, okay, because we don't really want to run the program. We just need to start the program so that I can examine the memory locations. All right, so now that we have a program running, L1 is not a regular, it's not a variable, okay? So you really don't want to use L1 as a variable. L1 as a label is the location. It is actually the location of the first byte, the least significant byte, or the first byte of the dot long, okay? So if you accidentally say print L1, it's gonna say it's just a label. It is really just this particular value, which is not of much help to you, okay? Because there's no type associated with L1. L1 is not a dot long. L1 is nothing more than a bookmark. It's nothing more than a page number. It doesn't care what is on that page or what is on that page and what follows. It just turns out that this is how we initialize memory. It is a dot long. It's taking up 4 bytes. Okay? So all of those ideas about types, okay, that you learn in C and C++, you kind of have to let it go in this class, okay? Because labels do not have types. Okay, it is just the location. L1 is just this location. What do you want to do with it? So print is not going to be very helpful because print assumes, print is useful only if you know what it is. But since we don't know what it is, it's not very useful. The other command that will be helpful in this case is called X, which is examine. Okay, so the X command is using this particular format, X/, and then you specify a format, and then you specify the address. The format is described as follows. You can specify an optional repeat count. In other words, you can say, if you don't say anything, it is the default is 1. Give me one thing. That's the default. But you can say, give me 20. So you can say X/20 and then something else. Go ahead.
As you said, L1 is just a label. So why it start from a third row from long?
Sorry?
So as you said, L1 just...
No, this is seen from the perspective of memory layout. In other words, this is just referring to the least, the byte at the lowest address of whatever this dot long thing is. So it's not seen from the value perspective. This is not the most significant byte. This is actually the byte that has the lowest address because we count from left to right. Okay, so getting back to the X command. Okay, so what you can specify next to the count, which is optional, would be O for octal, X for hexadecimal, D for decimal signed, U for unsigned decimal, T for binary, F for float, and so on. Okay, this part is controlling how you want to display it. Okay, do you want to display the content in what base? Base 8, base 16, base 10 signed, base 10 unsigned, binary? Do you want to interpret it as a floating point number or an address, and so on and so forth? In our case, it's easy. Okay, we just want to look at each byte. Well, we'll do a 1 first, okay, in hexadecimal. After that, you can specify the size. The size would use B for byte, H for half word, which is extremely confusing because half word in GDB is a word in the assembler, which is 16-bit wide. Okay, you just kind of have to remember that part. Okay, it's confusing because dot word is 16-bit in the assembler, but in GDB as a debugger, it is a half word. Okay, a half word is 16-bit wide. A word is 32-bit wide.
Okay. So,
Okay.
So in GDB, it's referring to the machine itself.
Yes. So dot word as the source code is 16-bit wide, but a W in GDB is 32-bit wide. Okay, so it's a little bit confusing. You just kind of have to keep that in mind when you're using GDB. Okay. So in this case, I want to use exactly Word because it's a dot long and it's 32-bit wide. So I want to display the entire 32-bit as one chunk this time. And then you specify the label, which is L1. It tells you where we are going to examine in memory. Are we kind of doing okay so far with this command? The way to formulate it. Yep.
What does the length look at?
It's a count. It means it'll give me one of the following.
Okay.
But you can specify like 20 and say, give me 20 of the following. So it will basically interpret the next 20 things. In this case, it are 20 words. Yes. So we just want to look at one, and then when we press the Enter key, it's not really surprising. Okay, it's just telling us that those 32 bits, okay, those 4 bytes, starting at location L1. If I print it out in hexadecimal, it is 001897F6, which is exactly how we entered in the .word directive. Is that okay so far? Okay. You just have to remember, this side is the address, this is the content at that address. But it is now printed as a 32-bit number. The next thing we'll do is we'll say, oh, okay, I don't want to look at this as a 32-bit quantity anymore. Give me this, the same thing, but this time I want to look at it as 4 individual bytes.
It will do the same thing.
So it would dump the 4 individual, it will dump the same location, in fact, the same byte, but this time it will look at it not as a 32-bit number, but as 4 individual bytes. And then when you look at it as 4 individual bytes, the left one has the lower address because it's listing from left to right. And when we press the Enter key, is that surprising? The least significant byte is F6. It has the lowest address. The next one up is 97. The next one up is 1A. The implicit most significant byte is 0. Because I never found out the actual most significant byte in the .word, which is unnecessary. Are there any questions about using the X command?
Would you still be able to do it in the print command?
The print command is a little bit tricky because you can cast stuff to do it, but it won't deal with the count, unfortunately. So the X command is the easy one because you can actually specify, I want to look at the next blah, 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 many things. And by the way, print it out in whatever format you want.
I just wanted to check to see if there's like a technical limitation.
It's not a technical, well, it is a kind of a limitation like that because when you look at the help page of print, it does not give you an ability to specify count. I don't think it can specify count. Okay, maybe preceded. Oh, okay, it can do the same thing. So maybe we can do it. Okay, well, I'll give it a try. For XB in this case, and we'll. But 4XB was what we used, right?
Yeah.
So we'll have to give it the address, which is L1. Size letters are meaningless. Okay, so we can't do that because it wants to get the type. It wants to get the size from the type itself. So we'll now have to cast it to a char pointer first. Item count other than 1 is meaningless. Okay, so that answers your question, doesn't it? So you can only print one thing at a time, and it's not dereferencing it, so you have to do the dereference it. So you can get to the same thing, but it's going to be
Go back to X.
yeah. It's going to be more trouble than it's worth. All right. So are there any questions about this particular sample program, which is nothing more than a label with a dot long? So what you can do is to do something like this to the program itself. You can always use a pound sign to comment out the instructions that needs to be filled in, and then examine the locations and find out how memory is laid out, and then use that as one step of your process. Yep.
I don't know if you're right. But so then, where we want to, for the assignment, where we want to be looking at the contents of the registers is EAX.
I'll get to that part.
Okay.
I'll get to that part. Okay, so are there any questions at this point? Okay, no questions? Okay, if there are no questions, I'll go ahead and write the next sample program. So I'm giving you all the individual pieces. Okay, this one is register immediate. Okay, register im.s. And the whole point of this one is to say, oh, how do we get something into a register? You have to use the immediate operand. Okay, so let's go ahead and do the whole thing so the program would actually assemble. So in this case, you can use a move instruction. The move instruction can take one of 3 suffixes. In this case, I'm using the L suffix for 32-bit. You will also take the W suffix for 16-bit or the B suffix for 8-bit. Okay? And we'll move on and talk about how a register is organized next. Okay? So we'll go ahead and move along to a particular expression. Now, whatever I specify here, whatever is after the $ and before the comma, can be any expression that gives you an integer. Okay, so if you want, you can say 0. Okay, that would just mean 0. Or you can say, oh, I want to know where underscore start is. Well, guess what? Underscore start is nothing more than a label. So you can always move that into a register if you want to do that. Okay, that's okay. You can even do something like that. I do not know why you would want to do it, but you can do it. You can divide an address by 2. I don't know why you would want to do it, but you can do it if that's what you want to do.
Do some tricky math.
You can multiply the thing to itself if you want to. Okay, to get the square of an address. And once again, I have no idea why that might be useful in any scenario that I can think of. But I can only think of so many scenarios. Okay, so the point is, it can be any expression. I'm just going to use a very simple expression here, which is just 0. Okay, moving into EAX. So the syntax of this assembler requires you to use a $ for immediate operand, because you are specifying the actual value that you want to copy into a register in this case. Are we doing okay so far with this? Okay. And when you name a register, you have to start with a % symbol. That is a part of the syntax. If you do not start with a % symbol, you will get an error message, but not from the assembler. It's going to come from the linker. Yep, go ahead.
Is there a specific meaning of a $ and a % there?
The $ means it's an immediate operand. Okay, and we'll talk about what it means without the $. Okay, go ahead.
The reference page doesn't have an entry for move L?
Move L is an instruction specific to the Intel architecture, and that's why it may not contain that. It's just copying from the left. The first operand is copied to the second operand. Each part is called an operand. So $0 is called the first operand, and then EAX %EAX is the second operand. The second operand is always the destination. That's the one that is being changed. Okay. And move long is a misnomer also. Okay, there's no such way. There's no way to actually physically move something inside the memory of a processor. So it's actually more like copy. Okay, it should have named copy instead of move. All right, so let's go ahead and put a no op here so we can stop on line 6, and then we'll run this program and find out what EAX has after this. Okay, and this is more for just getting used to GDB commands more than anything else, because I think we all know what the program is going to do. Here we go. GDB. Put a breakpoint on line 6. Run the program, and now there are several ways to look at the register EAX. You can look at EAX as $EAX using a print, and when you use print, you can also specify /x for hexadecimal and stuff like that. You can also use IR EAX, which is info register EAX, which will do the same thing. It will just give you the value of EAX. When you use IR, which is info register, you do not use a $ in front of EAX. When you use print, you have to use $ because it is not really a variable, it is an internal variable corresponding to a register. Are there any questions about this? No questions? Okay. Any questions before we move on? Yes?
I missed, what's IR again?
Info register.
Info register.
Yep. It's info reg.
Did you have to run it PGDB first?
Sorry?
Did you have to press run first?
Yeah, you have to run first. Because otherwise the processor does not have any context of this program which is supposed to be running. Because otherwise you cannot print a register when there's no process to ask.
Sure. Makes sense.
Okay. All right. So this is the second concept. And then the third one is this one. I would call it, I'll call this portal. All right, so this program is going to be about the same as the other one, except it's a little bit different, okay? So I'm going to start with a move out instruction with immediate operand, but this time I'm going to specify a kind of longer pattern, okay? We'll just start with do something that is very predictable, okay? In hexadecimal 1, 2, 3, 4, 5, 6, 7, 8, and copy that to EAX. But then the next instruction is move W. Move W is going to move only 16-bit. So with move W, you cannot specify a 32-bit register. And I'll draw a picture, on the whiteboard, which will explain, how you look at the registers. But I'll finish the program first, and then I'll talk about that. So in this case, I will copy, the hexadecimal number of ABCD into register AX, okay? And the last one is a move B instruction, and I'll go ahead and copy, I don't know, maybe 2, 1 into register AL, okay, there we go. And then a go up instruction here, so we have a place to stop. Okay, so it would appear that we have used 3 registers in this case, but that really is not the case, okay? We are using only one single register. That one single register is EAX. But what about AX? AX is a part of EAX. What about AL? That's a part of AX itself. Okay? So what you want to do is to actually have a picture in your mind when you refer to the registers. So let's say this is my EAX. The entire thing is EAX. Okay? It has 32 bits or 4 bytes, right? Okay. So I'm going to divide it into 4 bytes here. This is the most significant byte, M as uppercase B, okay, because uppercase B for byte, lowercase b for bit. Okay, this is the least significant byte, like so. Or if you want to count bits, this is bit 0 all the way to the right-hand side, and this is bit 31, which is all the way to the left-hand side. Okay. When you look at AX, it is a part of it, but which part are we talking about? It's a 16-bit number, so AX is only referring to the least significant 2 bytes. So the black portion is register AX. It's a 16-bit register. Yep.
So would like EX refer to the first 16 bits, or would that be something else?
The first 16 or the most significant 16 bits cannot be addressed independently. So the only way to get to the most significant 16-bit of EAX is to refer to the whole thing EAX. Is that answering your question? Only the least significant 16-bit has a different name. What about AL? And there's actually, it has a companion called AH. Okay? So if you look at this portion here, it is also known as AH. This is the high byte. And when you look at just this portion here, it is known as AL. Yeah, I use the L like this one, so it's not confused with 1. Okay? So that's why this program is called Portal, because the different names, AX, AH, and AL, they are basically just a different aperture, different portal to look into the same thing, which is still EAX. It's just a different part of EAX. Let me answer his question first. Okay, go ahead.
So when you use AX, does it automatically initiate the most significant bytes to 0?
No, nope, it does not touch it. Okay, when you overwrite AX, it does not affect anywhere else in EAX. when you address AH or AL, it will only affect 8 bits. It will leave the other 24 bits alone. That's a good question, very good. And let me go back to your question then.
And are there commands for the most significant bit?
The most significant byte or bit?
Bit,
Byte? Bit?
Yeah, are there commands like AH for?
No, there are no names for these 2 bytes individually. So there's no way to refer to the most significant 2 bytes of EAX independently. Only the least significant byte.
You can do tricks, like, you can.
Yeah, you can do
zero out
shifting
the bottom part.
and yeah, you can do some bit masking and stuff like that. But it doesn't come with its own name. Yeah. All right. So knowing this, okay, what is this program going to do? Well, let's figure it out. Okay. So the best thing, the most important part is you have to kind of predict what the program is going to do, and only run it through GDB to confirm your understanding. Okay, that's the way to run these sample programs. Okay, so I'm going to do it on the projector. Okay, so I'll do all of this stuff in the projector, and I'm just going to comment it. Okay, so EAX after this operation is going to be in hexadecimal 1, 2, 3, 4, 5, 6, 7, 8. Not exactly very exciting. Okay, after the second instruction, even though it is only changing AX, I want to keep track of the entire 32-bit. The most significant 2 bytes are not changed, because AX only refers to the least significant 16-bit, so only that portion is changed. It doesn't touch the most significant portion. So in this case, the least significant 2 bytes will now be A, B, C, D in hexadecimal. The third instruction is going to change EAX, but it will only affect the least significant byte in this case, because that is the only portion with the name of AL. So in this case, only the least significant byte is going to be changed to 2-1 in hexadecimal. So the entire number should be 1, 2, 3, 4, AB, and then 2-1 here. Is that doing okay so far? Okay. So once we have, kind of a basic understanding of the instruction, and we kind of think we know what this is supposed to do, now it's time to actually run this program to see whether it is going to do what it's supposed to or not. Yep.
How about the data that previously there?
Say again?
How about the data that previously there? Like 6, 5, 6, 7, 8 on the second line.
It's overwritten. Because AX and AL are basically referring to in the smaller parts of EAX. So when you overwrite it, whatever was there is going to be overwritten, is gone. Yep. So let's go ahead and link the portal. Node, portal. Okay, we can actually stop in every single line just to be sure. Okay, so we'll stop on line 4 first. Run the program. We can just say print /x EAX. This is before line 4 executes, so this is the initial value of EAX, which turns out to be 0. Single step, look at EAX again, and not surprisingly, it is 1, 2, 3, 4, 5, 6, 7, 8 in hexadecimal. Single step again, and look at EAX. It is now 1, 2, 3, 4, A, B, C, D. Now, this is also a good time to let you know that in GDB, you can actually access AX by itself. So $AX refers to just the smaller portion of EAX. Okay, so it can come in handy sometimes, so that you don't have to kind of do your own math to get to the least significant part. And obviously, for the same reason, you can print AL and also AH. Okay, are there any questions about this part of GDB? Because I have a feeling that this might be helpful in your homework assignment. And then we'll single step, this is the last instruction, and we'll go ahead and take a look at AL first, which is supposed to be 2-1, AX, which is supposed to be AB 2-1, and we'll go ahead and look at the entire thing, which is EAX. It is 1, 2, 3, 4, AB 2-1, just as we kind of predicted. Are there any questions about this part? Yeah, no questions. I'm going to pass the roll sheet around. This is one of the rare cases or rare days that I actually remember to do it. Yeah. Next time I have to draw like some kind of happy face or something that just kind of stares at me like, oh, okay. Okay. All right. So let's take a look at the homework assignment and see whether we have addressed how much we have done. We talked about dot byte, dot word, dot long, the definition of a label. We talked about the EBX, BX, and BH. And by the way, EAX, EBX, ECX, and EDX, they're all arranged the same way. In other words, with EBX, you can refer to this part as BX, BL, and BH. With ECX, kind of the same thing, just substitute the A with C. So the whole thing is ECX, this is CX, this is CL, and CH. Same thing with EDX. Okay? But those are the only 4 registers that allows you to do this sort of thing. Okay? D. Yep. All right. So we are done with the designation of long versus a word versus a byte. So that part is done. We are done with the immediate operand. The only part that we are not quite done would be these 2 operands. One is called the indirect operand, and the other one is called a direct operand. Okay? We'll talk about the indirect operand first, because we have seen it already. Not so much in the I386 instruction set, but in the architecture that we have talked about. Okay? So with this particular instruction on line 10, what it does is it will look at the content of EAX, but it's not copying EAX itself into EBX. It is it's using EAX as an address. It will go to the location, and then it will copy the 4 bytes starting at that location to EBX. It's called indirect. It's the same thing as dereference.
So the parentheses are the dereferencers? Or
The parentheses.
The parentheses that we have around.
Correct.
the
It's basically the
that's
same
all.
thing as a dereference, right? Yep. So if I were to do something that's dangerous, which is to kind of write the equivalent instructions in C, okay, which is kind of dangerous because we actually do not have types in this case. This is just the same thing as EAX gets whatever you specify, okay? This one, oops, yeah, this one is saying EBX is dereferencing EAX. Okay, so I'm not copying EAX, I'm copying whatever EAX points to EBX. Now obviously, since it's a move long instruction, it's copying 4 bytes instead of 1. Okay. The last one is kind of easy too. The last one is just if BH is getting whatever you specify here. Okay. What about this one here? This is called a direct operand, and the direct operand is kind of the same thing, but same thing as an immediate operand, but it's completely different. It's kind of the same in terms of syntax, but it's completely different in terms of meaning. In terms of meaning, it's somewhat like a combination of an immediate operand and an indirect operand, because whatever you're doing is you're copying, the underscore specifies an address, but it's a constant, okay? It's just an expression, it's a constant. So it would go to that address, grab 2 bytes, and put it into BX in this case. Are we doing okay so far with that concept?
Can you say that again?
Okay, the underscore on line 11 is going to be an expression that evaluates to an integer. Okay? We take that integer as an address. We go to that location, and then we copy 2 bytes from that location to BX in this case. Yep, go ahead.
So if you were to put like L1, it would go to L1 and take it to
That is correct. Yep. Okay. So let's go ahead and I will go ahead and write another. Yep, go ahead.
Is that an address within its own program space?
Say again?
Is that an address within its own program space?
It is an address within its own address space, correct.
Okay.
Yep. And every process has its own address space. So there's no way you can actually corrupt the operating system or anything else. Okay, so let's go ahead and write the next sample program, which is going to be the last one that you need. So we'll go ahead and do pretty much the same stuff here. Direct. Okay. So with this one, I'm going to specify L1 here and odd word 0x ABCD. Okay, so we'll just make this easy. Okay, and then we'll have move W. Okay, moving only 16-bit here, and we'll specify L1 but not anything else to BX. Okay. Put a no op instruction here. So once again, let me just explain what line 6 is going to do. Line 6, the first operand is L1 without the dollar sign. Okay, with the dollar sign it's immediate. Without the dollar sign, it is direct. Okay, so you got to remember that part. It's very easy to confuse one with the other one because syntactically speaking, they're very close, they're very similar, but in terms of meaning, they're kind of completely different. So what this one is going to do is it will use L1 as an expression. Now L1 is a label, and every label ends up with an integer value. So L1 all by itself is nothing more than just specifying an integer. But it will not copy that integer into BX. It will use that integer value as an address. Then it will go to the location where L1 is pointing to and copy those 2 bytes to BX. Okay? Are there any questions about this? Now, if I, yes, go ahead.
So L1 is a pointer now? So L1 is a pointer now in this condition? So L1 is a pointer now?
A point.
It's a pointer. Like
A
L1's
pointer?
like a pointer, basically.
L1 is not a pointer, it's just an address. Okay, this is how I would equate it in C. Okay, so this is really kind of dangerous because in assembly language programming, BX has no type. Okay, so I'm kind of making the assumption that this is a short int. Okay, so I'm just making that assumption here. So this is the same thing as doing this. L1 is an expression. That's kind of what it's doing. So it's using L1 as an expression, which is just nothing more than an integer, right? So the cast is saying, oh, by the way, this is not just any integer. Treat it as an address of a short int. A short int is a 16-bit thing. But I don't want to copy the pointer or the address itself into BX. I want to copy whatever is at that address into BX. And that's why there's the extra dereference, the asterisk symbol, to complete the meaning. Are we still doing okay so far? Yep.
Would you get an error if you use move long?
If you use a move long, you will get an error because the length or the width of the opcode, which is move long, does not agree with the second parameter, which is BX, which is only specifying 16-bit. So you will get an error from the assembler in that case, which is good, okay? Because you should always specify the width of an operation, to give the assembler an extra chance to catch possible mistakes. Okay, that's a good question. Very good. All right, so let's go ahead and write this program and see what it's doing. And I'm going to add another instruction here just to contrast the two. Okay, I'm going to do a CX here, and this one has a $sign. And I can tell you already, right here, the assembler will assemble without any problem, but the linker will complain. The reason the linker is going to complain is because L1 as an integer value requires more than 16 bits to represent. So when it's going to link line 7, it will basically say, hey, something is not right here, okay? Because L1 as an expression requires 32 bits to represent, but the destination only has 16 bits. CX can only store 16 bits. So are you guys okay done with Roshi? Okay, good. All right, so let's go ahead and just assemble and link the program just to see the linker complaining about this. Okay, the assembler is not going to complain. T-stats-o, direct.o, direct. Yes, see, the linker does not complain. Let's go ahead and link it. -o, direct.o. And the linker is complaining is only a warning. In other words, I'm still getting an executable because the linker is saying, hey, the integer value that you want to store, put into CX, is requiring more than 16 bits. But I will do the only thing that I can, which is truncating the most significant part of that number. Okay. So let's go ahead and run this program and see what happens. gonna say GDB direct. Oh, I forgot to do one thing. Oh, I have G steps. Relocation truncated to fit. No, it did not did not link it actually. Oh, okay. So it's not a warning, it's an actual error. So what I need to do is to make it happen. That would do it. Right? I'm hoping you still remember your bitwise operation from the floating point nightmare.
Yeah, when you are turning off the low light.
You're turning off the high bytes and preserving the low bytes.
Okay, yeah.
So I'm preserving the least significant 16 bits and getting rid of the most significant bits. So the result of the ampersand, the bitwise AND operation should give me something that will fit into a 16-bit destination. Okay. See, I said you can use any expression, right? Bitwise operation is definitely one of those. Okay, so let's go ahead and reassemble. Ah, it doesn't like that. Invalid operands and for ampersand. Okay. Well, there are different ways to do this. Let's see if we can do a mod. When you mod, you have to mod it with the power of 2. Oh, it doesn't like that either. Invalid operand.text and ASB sections.
No mod.
In parentheses?
Parentheses would make it immediate. Wouldn't it make it an indirect?
I don't think that's an issue, but we'll go ahead. Give it a try. Because it has not seen the comma yet, so it really should not get confused. But that's always possible. Nope, that's not the case. Oh, okay.
So wait, so those parentheses they don't always function as the indirect operator? Because you know that's online for.
You can put parentheses. It's complaining about the operator. I cannot apply that operator to L1.
No, my question is in the actual assignment, in one of the lines, I think or whatever, like 11, you have.
This is the assignment.
Yeah.
Let me look at your. Is it over here? Nope. Ah, okay.
Yeah, it's online.
It's still here. It is just I used the wrong folder.
Yeah, line 10. So
Okay.
there you said that the parentheses function as an indirect operator. So
That is indirect. Yes.
So back in our code, does the $sign negate the functionality of the, because when we put it in parentheses, shouldn't that then also be indirect operator? Back in the code example that you just wrote.
No, because it's after $sign.
That's what I'm saying, so the $sign.
So after the $sign, it can no longer be indirect. And besides, you can only specify a register inside the parentheses when it's indirect.
Only
you cannot
register.
specify any expression. It can
Okay.
only be
Registers.
a register. Yep. Okay, so let's get back to the other program, which is direct.s. I'm just struggling here to find out what I can do to get rid of the most significant bits. Doesn't look like it's possible. Well, we can get back to an ampersand. I don't think that's gonna work. I know the program is wrong to begin with. Invalid operands for ampersand. Okay. I'm just gonna do one more thing and see whether I can do it with other types of values. Okay. And see whether I know the result of this operation, but I just want to see whether it's the label itself that's interfering with the operation. I think it's the label. Yep, there we go. I can kind of understand why, because it can only keep track of offsets, so it can only +1, -1, but any other type of arithmetic operations won't work. And hey. Nah, that won't work. All right, well, so instead of doing this, I'm going to use a 32-bit version of this and turn it into loop long, okay? So in this case, ECX is really just fitting L1. Okay? All right, it's still enough, it's still sufficient to illustrate the difference between a move direct operand, which is the first one on line 6, and also in the move immediate operand. Okay, so we'll go ahead and take a look at this one. And sample link GDB direct. Put a breakpoint on line 6, run the program, and we single step. Take a look at BX in hexadecimal. Is that making any sense? Now, given that L1 is the label of the location where the least significant byte of the dark word is that making any sense? I just ran the instruction on line 6. Is that okay? That's the direct operand. Okay. Let's take a look at the second instruction. Okay, on single step using the second instruction, and now I take a look at ECX in hexadecimal, and that's what it looks like. Okay, that doesn't seem like anything that we have entered. Okay, how do you think it will relate to L1?
The same.
It will be the same. Exactly. So is this sample program illustrating the difference between an immediate operand as opposed to a direct operand? All right. So I think that's all the addressing modes that you need to understand for this homework assignment, and all the instructions also. Okay. And you have to kind of put everything together, starting with the goal of your homework assignment. So what I'll do next is to go back to the homework assignment. We'll take a look at the homework assignment, and I'll give you some general pointers to start with this homework assignment. Oh, it's about money. There we go. Okay, so with this particular homework assignment, the goal, the destination, is I want EBX as a register, 32-bit register, to have a particular value. And you look at that value, 38588 0604, and you say, where the heck do I find that bit pattern and put it into EBX?
That's a decimal number, correct?
I cannot answer that question because that's your homework. Okay. Yeah, because we kind of talked about it quite a few times already. You're just asking for confirmation. And by the way, there's a quick and easy way to find out what number it is and convert the bases. And you don't need a calculator. You just need GDB. Okay, GDB has a lot of interesting things that you can use for this particular homework assignment. Okay, so the first thing you have to do is to find out, okay, what is the content of EBX when this is all done? Representing things in a particular base is not particularly useful, so you want to do some base conversion, okay, to go to a particular base that is useful, okay? If you like zeros and ones, you can do everything in base 2, okay? Just do everything in base 2, as long as it is, all in the same base, and it's a power of 2, the base itself is a power of 2, then you'll still be okay. Okay, so that's the first thing you have to do, is to look at the bit pattern of what needs to be in EBX when everything is said and done. Is that okay? Second thing, you look at all the instructions. Okay, look at all the instructions that can change EBX, or at least a part of EBX. That will be instruction on line 10, line 11, and also on line 12. Some of these instructions is the only one that can change a particular portion of EBX. Okay, remember, a certain portion does not have any other name. Okay, so use that to lock down those instructions first. Okay? In other words, you look at a particular instruction and you say, oh, after this instruction, I know which part of EBX has to be a particular bit pattern. Then you look through the memory that is initialized. Okay, so everything between line 2 and line 5 inclusively would be used to initialize a chunk of memory. In other words, there will be a particular bit pattern. Okay, in fact, there will be how many bytes again? 3 plus 6 plus 12. 3, 6 is 9 plus 12 is 21 bytes, okay? So there'll be 21 bytes initialized in memory. L1 is the address of one of those 21 bytes. You kind of have to figure out which one it is, okay? But from that one location, you can access the other locations. And you just have to find out, how do I get that particular bit pattern into that portion of EBX? That will lock down one of the underscores, okay? And then you look at the other instructions and say, okay, now that we are done with that portion, and none of the other instructions will touch that portion, I'm done with that one. Then you look at, let's say line 11, okay? And you say, okay, line 11 is going to affect which portion of EBX? And then you say, okay, the next instruction, which is line 12, cannot change that part of EBX anymore, okay? So now you can say, okay, now we need to go back to the memory content and find out, how do I get that particular bit pattern into BX? And then the last one is actually the easiest, okay, because you don't really need to go to memory for the last one. the last one is the easiest one. Are there any questions about the general approach of this assignment? Yep.
What is the line 17 to 94?
Huh?
Not central.
Sorry, say again?
Yeah. What is this string commanding here for?
The last 3 lines.
The last 3 lines? The last 3 lines are exit code. You don't need to change any one of those. That's the same thing as exit 0 in C and C++.
So we, as long as we executed until 12, we got the value which is 3A5 something. That's we're done with that, right?
Okay, let me do this homework for you so that you know the flow of the homework assignment, okay? Okay. Now, since I cannot give you the actual solution, I'm going to comment out all of these lines, and I will substitute it with a bunch of very useful instructions. Okay? So the way you test this program and debug this program is going to be like this. Okay? You save the file, and then you do an AS to assemble the file, bunny.o, bunny.s. How you want to name your object file and your executable is entirely up to you. Okay, I don't really care, but you do have to preserve the name of the source file. Okay? ld-o bunny, which is the output, the executable, bunny gunny. Now we are starting to talk about Bugs Bunny stuff. GDB bunny. So one way to debug this program, if you feel confident about your code and you just want to look at the final product, this is how we do it. Put a breakpoint on the label. You can put a breakpoint on the line number if you want to, but if you know the label name where you want it to stop, you can do that as well. And that's why I have check here as a label, because the intention is I will grade this at least partially using a script. So my script in GDB is going to do the same thing, which is putting a breakpoint at the label check here. And then you can just go ahead and run the program. And it's stopping at the label check here. So at this point, you can now say print EBX. Oops. Oh, I just set up a breakpoint. No, I did run it. Oh, $EBX, that's why. Okay. Print $EBX. Darn, I'm not done with my homework yet. But that's the general workflow. So you do the part of the program, and then you set up a breakpoint, and then when the program stops at the breakpoint, then you either single step, or you can examine the registers to see whether, okay, I think I'm getting close, okay? I would work on this one one step at a time, okay? The first 2 instructions are considered basically one instruction, because they are closely related. In other words, okay, let me just kind of revert the program back to what it used to be. Okay, so line 9 and line 10 are kind of together because line 9 itself is not going to change EBX. So if you want to change EBX in a particular way, you kind of have to run both of those instructions before you can look at EBX and go like, oh, okay, I think I got is what is supposed to be EBX. Okay, so I'll just go ahead and give you a quick rundown of all the concepts that we have talked about today. And I can refer to this program as we talk about it. Lines 2, 3, and 5. They are nothing more than just saying, oh, I want some of the memory locations initialized and reserved. Okay. Line 4 is the definition of a label. And remember, a label is only the address of 1 byte because the i386 architecture is byte address. Okay? And there's no such thing as type in assembly language program. So also keep that in mind. We talked about the move instruction, which is actually a misnomer, which means it's a wrong name because it really should have been just copy. It copies the first operand to the second operand. In this case, the second operand is always a register, so there's nothing really special about the second operand. As far as the first operand is concerned, line 9 has an immediate operand, line 10 has an indirect operand, line 11 has a direct operand, and then line 12, once again, has an immediate operand. All right. We also talked about the Endianness of an architecture, which is referring to the ordering of the bytes. When you want to store a multi-byte value, where is the most significant byte, where is the least significant byte? We talked about the components of a particular register, EAX, EBX, and ECX, and EDX. They are all organized in this particular way. You can refer to all 32 bits. You can refer to the least significant 16 bits. And of the least significant 16 bit, you can also refer to each individual byte if you want to. So they're basically just names for individual parts, but they are really actually parts of the same register. We talked about what you can specify in after the $sign and also in the direct operand. Just basically any expression, and it can involve calculations as far as a label is concerned, but only with addition and subtraction. Okay, because we tried ampersand, the bitwise and didn't work. Okay. So are there any questions at this point? No questions? You have 1 week to work on this homework assignment, and we do have class on Thursday. So if you get started early, then you will still have a chance to ask questions about this homework assignment on Thursday. I hate to nag like a dad, but since I am a dad, so I have this, kind of notorious habit of telling people, start early, okay? If you start early, it's not any more work than starting late. And the good thing is you guys are not my daughter, and you don't give me that look, like, yeah, I know what I'm doing. Go away, buzz off.